Hello students, welcome to EPG Pathshala. I am Mahavir Singh from Physics Department, Himachal Pradesh University, Shimla. Today we are going to talk on module Superconductivity 4th under the paper Solid State Physics. So student, let us see what we are going to learn in this module. Learn about the macroscopic quantum interface of superconductor using Jobson junctions. Learn about the fact that diffraction and the interference effect in the experiment of Jobson junction will lead to long period variation of current. Learn about difference of conduction mechanism in conductors and superconductors. We will also learn about the existence and stability of Cooper pairs and the fact that how they are formed. Macroscopic quantum interference. From classical mechanics, as we know that tunneling is not possible. This is well known fact, and in quantum mechanics tunneling is possible. So this macroscopic quantum interference, so sometime there is confusion. On one way we are saying that quantum interference, on other hand we are saying macroscopic. So basically quantum behavior at macroscopic level rather than at atomic level. So it is different. In ordinary situation we apply quantum at atomic level, but here in superconductor we are talking about macroscopic quantum interference. Macroscopic quantum interference. This microscopic quantum interference consists of single particle quantum mechanics and many particle quantum mechanics. So macroscopic quantum state occurs when the macroscopic number of electrons, which is large in number, is assigned to a single wave function. Macroscopic quantum phenomena in superconductivity differ from the normal physics, where normal motion, thermal motion marks the quantum properties and thereby no quantization effect occur on macroscopic scale. No role of quantization as we talk about macroscopic scale. In superconductivity, macroscopic quantum effects are easily observable and lead to the quantization of flux through loop, and also define the concept why electrons form highly correlated system. So basically this correlated system, highly correlated system, is linked with the quantization of flux. So remind Jobson junction, which expresses current as a function of phase difference as well as flux. The phase difference around the closed circuit, which encompasses the magnetic flux, is given by, for B equal to 0, that is in the absence of field, theta 2 minus theta 1 is equal to delta, and for B equal to non-zero, theta 2 minus theta 1 is equal to 2 small e, which is electronic charge, over hc, where h is the Planck's constant, c is the velocity of light, and phi. The magnetic flux through the circuit is the sum of the total fields, that is both external field as well as due to the current flowing the circuit. So let us consider a circuit containing two parallel Jobson junction, small a and small b, without applying any voltage as shown in figure 1. Let the phase difference delta A between point 1 and 2 through the junction A, small a, and phase difference delta B between point 1 and 2 through the junction small b. If there is no application of magnetic field, then these two phases must be equal. So this is now important condition here. In the absence of magnetic field, two phases are equal. Then making use of solenoid normal to the plane of the paper, so special design of solenoid, and lying inside the circuit of two junction, flux can be passed through the interior of the circuit. Then the phase difference is given by theta B minus theta A equal to 2E over H cross C into phi, and delta B equal to delta 0 plus E by H cross C phi, and delta A equal to delta naught minus E by H cross C phi. And we can also visualize in figure 1 how it vary on 2 points 1 and 2. The total current through each junction will be given by, that is J total equal to JA plus JB, and J total comes out to be J naught sine delta naught minus E over H cross C phi plus sine delta naught minus E phi over H cross. So we got two contribution, whereas in earlier module as we were discussing Jobson, there was only one contribution. Condition for maxima is E phi is equal to H cross by C is equal to N pi, where N is NA integer. So this is condition for maxima, and the current versus magnetic field is represented by figure 2 with periodicity, different periodicity. In figure 2 we can see that when periodicity is 39.5 milligauss and Imax is equal to 1 milliampere, when periodicity is 16 milligauss and Imax is equal to 0.5 milliampere. So how current vary, it is mentioned in figure 2, that how periodicity affect the variation of current with magnetic field. The interference effect between two junctions produce short range period variation for the long period variation diffraction. So let us talk about applications of macroscopic quantum interference. The first most very important application of this superconductor is the SQUID. SQUID means superconducting quantum interference device, and this SQUID it is of two type. Its discovery, it was discovered, this DC SQUID was discovered in 1964. It was invented by Robert Jaklevic and John Lambe, Arnold Silver and James Ford. The basic principle of the this DC SQUID is that small change in magnetic field produces a variation in flux quantum. So basically it is flux quantization. The basic principle of SQUID is the flux quantization, the production of flux quantization when there is even very small change in magnetic field. That is why this SQUID, we call this SQUID can detect even minute, very tiny magnetic moment also, even at very low temperature. So the basic construction is the superconducting quantum interference device consists of two superconductors separated by thin insulating layer to form parallel Jobson junctions. The application of macroscopic quantum interference types. So there are principally two main types of SQUID. One is RF SQUID, have only one Jobson junction, and other is DC SQUID, have two or more junction. Both these techniques more difficult and expensive to produce, and both are much more sensitive. RF SQUID is basically very important technique which nowadays people are using. This SQUID, basically RF SQUID, based upon this superconducting Jobson effect, utilize only one junction rather than 2 as that of case of DC squid. This is quite less sensitive than DC squid. However, for most of the experiment which involves the measurement of small magnetic field, RF squid are very common to use. The advantage is that it involves little bit cheaper and easy manufacturing technique. This RF squid, the basic purpose of this RF squid is to measure magnetic moment at very, very low temperature. If we compare squid with VSM is vibrational magnetometry. So vibrational magnetometry is effective up to 72 Kelvin. It can measure the magnetic moment up to 72 Kelvin, and we can go up to high temperature, whereas in RF squid it can goes up to 4 Kelvin. We can measure the magnetic moment up to 4 Kelvin this squid, but definitely this is costly equipment and it need lot of maintenance and careful precautions, and so for measurement of magnetic moment at different temperature, especially at low temperature, this RF squid is highly useful, and it is useful whether we talk about magnetic materials, especially ferrite or multiferroic materials, also DMS material, especially zinc oxide, then special kinds of magnetic semiconductor at low temperature, and also in biological area, especially for the hyperthermia technique, this RF squid is highly useful so far as the measurement of magnetic moment at very low temperature. So this RF squid, it is basically very, very important technique, and this RF squid is different from DC squid, and its working principle works on AC Jobson effect. It utilize only one junction rather than two, that of case of DC squids. This is quite less sensitive than DC one. So however, for most of the experiment which involves the measurement of small magnetic field, RF squid are very commonly used. But the advantage that it involves it little bit cheaper and easy manufacturing technique. So RF squid, if we compare both these equipment are efficient in their respective area, both these equipment uses the superconducting principle, that is superconducting kind of technique, whether it is Jobson effect of one junction or two junction. So both these technique are very useful, especially for material scientists. DC squid. DC squid was invented by scientist Robert Jacquick, John J. Lamb and James and Arnold in 1964. The central part of this device is a ring made of superconducting material with one or more Jobson junction in parallel to each other as shown in figure. In the absence of any magnetic field, the current which enter in the loop is split into two parts equally. But in the presence of small magnetic field H equal to B by mu naught, a screening current gets circulated in the ring because Jobson junction limit the supercurrent which can flow across the ring. This current is enough to generate the magnetic field which cancel the effect of applied flux to the loop. The setup current has the same direction as that of bias current, but only in one branch, and has opposite direction in the second branch. Whenever the current exceeds in one branch, then there will be the appearance of voltage across the junctions. When external flux is increased by, let us say, phi naught by 2, that is half of the magnetic flux quantum number, then flux enclosed inside the ring is not screened. As we know that the flux inside the superconducting ring must be an integral multiple of the magnetic flux quantum number. So squid must increase the flux to the value of phi naught. So thus the critical current oscillates as a function of the applied magnetic flux. If the value of input current entering into the ring is more than the resistive mode occurs squid, that is, in this case voltage becomes the function of the applied magnetic flux and its period becomes equivalent to phi naught as shown in figure 4. DC squid offers the IV characteristics hysteretic so as a shunt resistance is connected across the junction to eliminate this hysteresis. The screening current is the applied flux divided by the self inductance of the ring. The change in the flux can be converted into change in voltage by using Ohm's law, that is delta V is equal to delta E into R. Since delta E is delta phi by L, so delta V becomes equal to delta phi by R by L. In the above equations, L is the self inductance of the ring. If we go through this figure 3 DC squid, the junction 1 and junction 2 are separated by thin barriers which is red in color, and bias current enters split into two equal halves along the two junctions. So direction is shown, and in figure 4 voltage response to the squid is shown, which is oscillatory in character. On x-axis it is phi by phi naught, where phi is the phase, and delta V y-axis is the voltage which is sinusoidal in character. DC squid, this DC squid we use only one or more Jobson junction, but the condition is the both junctions are parallel to each other. Now Cooper pairing. Cooper was the first scientist who linked this instability to the small attraction or interaction between two electrons which reside near Fermi sphere. In the time scale of electron, lattice start deforming very slowly as shown in the figure. Lattice gets deformed up to maximum level within 10 to 13 seconds after electron has passed through it. So basically it is we can visualize from the figure that how when electron is moving, how this lattice deformed, and at the same time the this deformed lattice, how it is attracted. It provide the attracted potential, and this potential is the responsible for the formation of Cooper pair. Within this time, the first electron traveled approximately 100,000 angstrom. The positive charge of the deformed lattice, can then attract another electron without feeling the Coulomb repulsion of that electron which already has passed. So due to phonon, an attractive interaction start to build up a pair time reverse quasi-particle state. So basically they form a quasi-particle state. So student, let us now summarize what we have learnt in this module. One or more Jobson junction can be used in the experimental arrangement to understand the macroscopic quantum interface in the superconductors, and through this the device which is well known as squid, through which we can detect the magnetic moment, even minute magnetic moment, by on the principle of flux quantization. Then the phase difference relationship and the variation of current with the magnetic field explain the long period and short variation of current in the parallel combination of Jobson junction. The circuit containing two or more Jobson junction are termed as squid, and macroscopic quantum interface is the main phenomena occurring in them. The type of squid are common, which differ in their operation and thereby differ in their sensitivity also. The different type of squid can be utilized for the magnetic field measurement depending upon the sensitivity of the problem. Even today in market there are refined squid machine which can even detect the magnetic activity in the human brain. So squid is basically the major technology which we can derive from the superconductor through this Jobson junction effect. The Cooper pair, which is cause of conduction mechanism in the superconductor, consists of two electrons having opposite momentum and opposite spins. The two electrons of Cooper pair can form a bound state through weak attractive interaction through lattice. So in ground state of superconductor, all electron form the Cooper pair and all Cooper pair are in the same quantum state. Therefore, the superconducting state is represented by single symmetric and nodeless wave function that extend over the entire volume of the surface. Thank you.